This video is a quick summary of our research into GPS-denied navigation using synthetic aperture radar and the Range-Doppler algorithm. This work was performed at Utah State in cooperation with Sandia National Laboratories. This work is motivated primarily by the growing popularity of UAVs and automated engineering applications. For many of these applications, GPS is integral in project success. However, GPS can be made easily unavailable, whether by the environment or by intentional tampering. This motivates the use of GPS-denied navigation. For this research, synthetic aperture radar, or SAR, is used to formulate measurements for an inertial navigation system. SAR is a method of creating images from radar data collected along some flight trajectory. The image in the top right shows what the raw radar data could look like for a given flight. That raw data is then processed into images of the ground, such as the image in the lower right. Many algorithms exist to process the raw data into SAR images, but the algorithm we use is the Range-Doppler algorithm, primarily because it makes use of Fourier transforms, which makes it computationally efficient, and it means it could be used on smaller platforms with potentially less computational capabilities. To summarize our work, we set up a measurement model based on SAR images, altimeter measurements, and known target locations to produce measurements for an INS based on an indirect extended Kalman filter. The navigation system and measurement model were simulated using a Monte Carlo analysis, and then after simulation, the system was verified using real radar data. For our measurement model, SAR images are formed from a flight line using navigation information containing estimation errors. The estimation errors cause defocusing in the images, which must be corrected with an autofocusing algorithm. The autofocused images are compared to truth information from the known ground targets. Offsets in range and cross range are then measured and coupled with altimeter measurements, and then these measurements are fed into the INS. To simulate the system, a flight line was created over a ground scene of randomly placed reflective targets. Navigation errors are introduced and allowed to propagate through the flight line. SAR measurements were taken and applied to the navigation solution, and results were evaluated. The simulation was run several hundred times for a Monte Carlo analysis, and the results are shown here. The top row of figures shows estimation errors for position, and the bottom shows velocity estimation errors. The figures show that the position estimation errors are bounded within about 3 meters, and velocity estimation errors are bounded within about half a meter per second. The same system was applied to real data collected near Utah State University in Cache Valley, Utah. Position and velocity estimation errors are again shown here. They behave similarly to the simulated case, with less than 3 meters of position estimation error and less than half a meter per second of velocity estimation error. For more details, more plots of results, information about our methods, models, procedures, please refer to our paper entitled GPS-Denied Navigation, aided by synthetic aperture radar using the Range-Doppler algorithm. Thank you.